friends, Miss Kelly here with the Grimes Public Library. Do you know what your eardrum popping, boiling a pot of water, and blowing up a balloon all have in common? They all deal with pressure, air pressure. And that's our topic for today's Spring into Saturday, under pressure.
All right, friends, before we start our experiments, let's get into some definitions. Pressure. Pressure is a force that is applied over an area, a specific defined area. And that's a distinction that we want to make sure we understand. Let's use the example of using snowshoes in the winter. If you're walking in the snow, and it's very, very deep snow, here's our deep snow, and you're walking along in your regular boots, you're applying the force of your body into this deep, deep, deep snow at a very small point underneath your tiny little boots. So this is a pressure coming down on these tiny little points of your boots. And it will cause you to sink because the force you're applying is over this tiny little area. But if you get yourself a pair of snowshoes, now you're applying that same force downwards into this deep, deep snow, but you're applying it over all this big area. And so now the pressure is not as much that's forcing you down, and all of a sudden you're able to walk on top of the snow.
So now we know that pressure is simply a force, a push or pull on a certain surface. And now we're going to talk about particle pressure. So we're going to go very, very, very tiny into those tiny little molecules, chemicals that make up everything around us, gas, liquids, and solids. Starting with the solids, you will notice that the particles that make up a solid are very tightly packed together. And that is what forms the solid in its shape. So a solid can be anything from the t-shirt that you're wearing to the chair you're sitting on, the ball that you play catch with. But all those little particles inside that solid are not sitting still. They are moving. You just can't see them move. They are moving back and forth very, very quickly, vibrating, and they create pressure in that solid, pushing back and forth against each other and in the shape that they have created. The same is true for liquids. Liquids, you'll notice the particles are a little further apart. This gives them more space to bounce around, bump into each other in the container that they're in. And so like your glass of milk, your water, juice, whatever you want to think about with liquids, they're also creating a pressure amongst themselves, all those little particles inside, moving back and forth. Gas particles also move back and forth, but notice they are further apart more than liquid and even more than solid. And so they're moving even faster. So gas particles have the most energy, liquid have kind of a medium energy, and solids have the least energy, but they are always moving. Now, gas particles are the ones we want to focus on today because those are those invisible ones in the air around us. And they are pushing all over, bouncing off of things and bouncing off of us and creating pressure. Or when we talk about the atmosphere around us, we are talking about atmospheric pressure. So we're heading out into space. So let's take a look at a picture from outer space. Here is our planet Earth here, is the outer line of the corner edge here, and then you can see the moon way out in the middle of space there. You'll also notice this blue kind of misty line. These are air particles. This is the Earth's atmosphere that you can see, the air particles that surround us, protecting us from radiation from the sun and helps control the weather. Notice out here in the black of space, there's nothing. It's black, and that's because there's no air in space. You can't see anything. So remember, air is made up of tiny particles, just like we talked about. So all these little tiny particles are hanging out in this atmospheric layer around our planet, and gravity is pushing down on those particles. Those particles are bouncing around, they're bumping into each other, creating pressure, atmospheric pressure, and then they're being pushed down by gravity to the Earth and pushed down towards us. Now this is what we call our atmospheric pressure. So let's take a look back on Earth, moving to the outdoors here. It's just, we have a little camper out here in in the woods and Mr. Red. And Mr. Red is going to go camping, and we will take a note of how much air or atmospheric pressure is pushing down on him. So remember, we have air all around us, can't see it, invisible particles. But if we're going to focus on just what's pushing on Mr. Red, let's color in this little strip or column. This is the air pressure that goes all the way up to that blue strip, to the outer space, that is pushing down on Mr. Red. But if Mr. Yellow decides to go camping up on the hill, we will note that Mr. Yellow is not going to have quite as much air pushing down on him because he's missing all this below him where Mr. Red is. So Mr. Yellow is standing up here on the hill, and he is going to get some air pressure too. I'll grab the right color for Mr. Yellow. Here comes the air pressure, but notice it's maybe about half of the amount of air that's pushing down on Mr. Red. So we have less air pressure as we're going up towards outer space, as we're climbing up in elevation or up in altitude. And this is similar to when we're driving a car up a hill or going up in an airplane. Now, if we're going to take it to extremes, let's go hiking, mountain climbing, all the way up to the top of this peak. We have Mr. Green up there. Hopefully you guys can see him okay. And notice his air pressure is even less. It's only going to be the part right above him up until that little atmospheric space that goes out into the black of space. So what does this have to do with our ears popping? Remember I told you we were going to talk about that. So here's the inside of our ear. You can see the middle part of our ear here, there is a eardrum. And this is the part that can move back and forth, and it vibrates to help us hear, which is really important. And but it can cause some discomfort if you experience ear popping when you're going up in an airplane or down in an airplane, changing in that elevation or altitude, because what's happening is we're changing our air pressure. There is a difference between the air pressure on the outside of our ears and the air pressure on the inside of our ears. So if we think about that, let's think about the camper that's down outside. He's Mr. Red. We're going to put red dots here inside the body. So this little eustachian tube that I'm drawing dots in, this tube runs down to our throat, connects to our mouth, and the rest of our body. So if we are down camping, we have this air pressure on the inside of our body. But if we're not opening our mouth, speaking, not chewing, not eating, not yawning, now as we're climbing up very quickly in an airplane or very quickly on a road that's climbing up a very steep hill, the air pressure on the outside of our ear becomes more like Mr. Green, who is up high on the mountain. So the air pressure on the outside of our ear is low, while the air pressure on the inside of our eardrum is high. Now, what's going to happen? It pops our eardrum out. And this can make it hard to hear. It can be uncomfortable. And we want it to get back to equilibrium. In other words, we want the air pressure to be equal on the in and out. How do we do that? We just have to open our mouth, friends. Open our mouths, chewing gum, eating, yawning, talking, sometimes even swallowing can cause a sort of a pressure release. So it's going to allow those low pressure particles from up high in the mountain now inside our body, up inside, and it's going to equalize that pressure on our eardrum and pop it in the right direction. So now we can hear again and we don't have any more uncomfortable ear popping. And now let's check out the balloons. So what is it that allows someone to blow up a balloon? Well, we have atmospheric pressure pushing on everything, and it's pushing on the balloon. In order for the balloon to get blown up, I have to blow enough air pressure inside the balloon to overcome the atmospheric pressure that's pushing on the balloon and make the balloon get bigger. Let's give it a whirl. And I did it. Quiz time. What do you think? How'd you do? Did you get the answer right? Up next, let's talk about boiling water. What does that have to do with atmospheric pressure? Well, first let's examine what happens when water is boiling. We have heat underneath our pan of water, and the water is heating up, and those little particles in there are getting more and more energy and excited as they're bouncing around. So excited that they actually change state, and we become from liquid water into water vapor or gaseous water. And those water bubbles will then rise up and pop out of the water, becoming water vapor in the air around us. But what allows it to do that is that it has gained enough pressure inside those water vapor bubbles to overcome the atmospheric pressure pushing down. So if we think of our camper again down on the ground with it, there's a lot of air pressure pushing down, that huge red column of air pushing down. The water has to gain enough heat, enough energy of air pressure inside those water vapor bubbles to pop out and overcome the atmospheric pressure. But now if we draw our attention up to the upper right corner, there's another little pot boiling. This is the camper that's up high on the mountain. Notice the green pressure pushing down is a lot less than the red pressure for the camper that's down on ground level. So the water will not need as much pressure in its water vapor bubble to overcome the atmospheric pressure up high on the mountain. And the water will actually boil at a lower temperature. Scientists can actually make water boil at room temperature with the right equipment. Atmospheric pressure, pretty cool. Let's get started with some experimentation so you can have some fun at home. Our first one is called the fountain. For this experiment, you're going to need some Play-Doh, a straw, and an empty water bottle. Put some water in the bottom of your bottle in your straw and then try to make a tight seal around the top of your bottle. Blow into the straw. And when you do, this will create a fountain of water coming back out, as long as you have a tight seal. So when you're blowing in, the air has no place to go, and the pressure that you're blowing into the bottle will push the fluid, the water, back up the straw. With enough pressure, that water will shoot right out of the bottle like a fountain. Up next for experiment 2, we're going to make some divers. Using that same water bottle with a tight cap, some straws, and paper clips and scissors, and a cup of water for your testing. Take your straw, fold it in half, and cut it into a smaller length. Now we're going to bend your paper clip out so that it will insert into the ends of the straw, holding the straw in its bent position. This is our diver. When we place it in the water, there will be an air bubble at the top of the straw that allows it to float. Now here, it's floating a little too much. In order for my diver to work, I want to make sure that it sinks in a cup of water. So I'm adding some weight to it by adding some paper clips. You might need to add more or less paper clips as you're experimenting. Make sure that your diver hits the bottom of your cup with an air bubble at the top in the loop of the straw. Now it's time for the actual diver. Put it into your bottle filled all the way with water. Notice we have so much water it's spilling out, and then we cap it tight. Now the only air inside this system is the tiny air bubble at the top of your straw. So when I squeeze it, it's going to create increased pressure on that tiny air bubble at the top. And when it does, the air bubble decreases in size and the diver drops down to the bottom of your bottle. This is a really fun experiment. It might not work the first time, so don't give up. Remember, science is all about trial and error and trying new things to solve problems. So keep trying until you can get your diver to bob up and down with a gentle squeeze on your bottle. And for our final experiment, we have the leaky bottle. For this one, you can use the same water bottle that you used in the others with a tight lid, and then grab a thumbtack. Use the thumbtack to poke some holes in the bottom and sides of the bottle, tiny holes. Then fill it up with water and cap it quickly. As you tighten and release the cap, what happens? Oh, pressure, pushing down on me, pushing down on you, under pressure. I hope you've had fun exploring pressure with Miss Kelly and the Grimes Public Library.